Welcome back. I hope you had a good break. We are going to start by revisiting or going back to, we're not revisiting anything, but we're going to go back to some carbonyl chemistry. So we're going to start to talk about carbonyls again. We're going to view this through, we're going to find some new nucleophiles and we're going to add them to carbonyls. So the addition to carbonyls is going to be stuff that we've seen before. What we're going to focus on today is we're going to really focus on what are these new nucleophiles that we're going to use to do that. Okay. So the nucleophile that we're going to learn to use is going to be the enolate. And so the first thing we need to do is to define an enolate. An enolate is what happens when an enolate is formed when an H plus is removed from the alpha carbon of a carbonyl. Okay, so if we have an aldehyde, so let's say that we have an aldehyde that looks like this. The alpha carbon is this carbon right here. It's the carbon next to the carbonyl, right? So the carbonyl carbon is the carbonyl carbon, and then the alpha carbon will be the next one over. So there is a hydrogen attached to, well, there's two hydrogens attached to it, but there's only one that we're really concerned about. There's a hydrogen attached to that alpha carbon in this case. And so if we treat this with a base, we can do a Bronsted-Lowry acid-base reaction where the base removes the hydrogen and it makes a negative charge on that alpha carbon. Right? And so then you're going to get your conjugate acid, right? It's going to be the base plus H plus, and you're going to get your conjugate base, which is going to be a negative charge on the carbon. And now if you think about this, you would say, well, negative charge on carbon isn't a terribly favorable thing. Carbon is not very electronegative. So why would this reaction occur? And the answer is always is going to be resonance, right? We have a resonance stabilized anion here. And so this is our enolate. This is our enolate right here. And it's resonance stabilized. And so whenever we think about this acid-base reaction, the driving force for this acid-base reaction is that we make a stable base, and the reason that the base is stable is that we can draw this resonance form where you have a negative charge on the oxygen and a carbon-carbon double bond. So this is actually the more common form of an enolate. If you talk to an organic chemist and you say, if you ask them to draw an enolate or whatever, the form of the enolate that they're going to draw is going to be this one with a carbon-carbon double bond and a negative charge on that oxygen. Right? But the way that we get to this is we remove the hydrogen from that alpha carbon, we form the pi bond, and we again break the carbon-oxygen pi bond and push those electrons up onto the oxygen. Right? This is familiar. We've seen that kind of breaking of the carbon-oxygen pi bond before. What we did before was we added a nucleophile, right? So your nucleophile came in, it added to the carbon, it broke the carbon-oxygen pi bond, and pushed electrons onto the oxygen. This time we're doing the same thing. We're pushing electrons up onto the oxygen. We're making an additional lone pair on that oxygen. But the way that we're making that happen is by pushing electrons from the neighboring carbon and making a pi bond here. Right? So most often when we draw the formation of an enolate, so let's say that we have acetophenone here, and we treat that with some base. I'm just going to use sodium hydroxide. Okay. That's going to come get one of these hydrogens. We're going to make the pi bond, and we're going to push those electrons to the oxygen. We're going to do kind of all of that in one go. And what we're going to end up with is the enolate form, which looks like this. So this is how we make enolates, right? The way to make an enolate, is take a carbonyl compound, and it doesn't have to be an aldehyde or a ketone. It could also be an ester or an amide. We will use enolates of all of these things, right? So we'll get lots of practice making enolates. Carbonyl compound plus base, right? This is how we make an enolate. So that's the how of it, right? And the next question, of course, is the why. Why are we doing this? Why would we make an enolate like this? And the answer is that we now have negative charge on that oxygen. Remember what happens when we break that carbon-oxygen pi bond and put electrons on that oxygen? When we have a negative oxygen, the next thing that usually happens is we reform the carbonyl and start pushing electrons out, right? We've done that by losing a leaving group. That was all the carbonyl substitution stuff. This time what we're going to do is we're going to remake the carbonyl, right? And this double bond, this carbon-carbon double bond, is then going to be a source of electrons that will then go out and add to other things. So in the next video, we're going to see a couple of quick examples of enolate chemistry, things that carbonyl enolates can add to, and then we'll go on from there. So stay tuned for that.